everybody. As usual, I'm your host, Bobby, and welcome back to Bob's Jobs. Today is a very special interview because we are in person in the Emory University Science Labs. And I'm interviewing Dr. Burton and Dr. Michelle, and we're going to do some experiments.
All right, Bobby, why don't you come over here? We'll show you kind of two really simple demonstrations of how fluids make instability. So the first one we're going to learn about is how fluids can make channels and what we call fingers. So you can imagine, water spreading over a plane. It doesn't necessarily spread uniformly. It makes little rivers and little areas. You can see this after a rainstorm. But we're going to try to demonstrate in the lab, and I'm going to have you do it. But first, I need to pour this special viscous fluid in our Petri dish here. And this is something called sodium alginate. When we put some blue dye on it, something special should happen. So this is just blue food coloring, and I want you to take this little eyedropper.
Oh, that looks so cool. It looks like an eye.
Yeah. What we're studying here is something called mocha diffusion. It's actually an art technique when they put different kinds of dyes on a wet clay on the outside of porcelain. It forms all kinds of beautiful patterns. And this is just a laboratory mock-up of the kinds of things that you can get. You see all those little protrusions around the edge? That's an example of an instability. So the kinds of questions we ask are, well, why are they that length? Why are they that size? What determines all this? And this helps us inform the way we see nature form patterns around us.
Yeah, it looks so pretty. It reminds me of like whenever frost goes up on my windows, how it makes that pattern.
That's right. So whenever you have a freezing front, so you have an area that's ice and an area that's liquid water, you can have these types of dendritic patterns form as well. Now we're going to make you a souvenir to take home with you. Yeah. So this is some 3D fabric paint, and what I want you to do is take 3 dots and put them in a triangle very close to each other in the center. Now put a big blob of pink in there too.
That looks cool.
Now I want you to push your hand on that. We're going to squish it together, and I want you to put a lot of weight on it, right? And hopefully we can get a little messy. There you go. Now push it out the sides like that. Now, this is where the instability happens. So when we pull this apart, just pull it straight up.
Whoa.
So this pattern naturally formed whenever you pull it apart. So the fluid self-organizes itself into these dendritic patterns just because I pulled these things apart. And we write down mathematical equations to describe this stuff, but it doesn't quite capture the beauty of what you can see.
Yeah,
So we can put this here and let the paint dry, and then we'll make a keychain out of it.
I like it. That looks awesome. You know what it reminds me of? It reminds me of your finger. Like if you zoom up on your finger in the microscope, it looks like that.
Oh, you're saying it looks like a fingerprint. Yeah, and if you did this over and over and over again, you would never get the same 2 patterns twice. So an interesting thing about instabilities is they're sensitive to the microscopic fluctuations that are happening that get amplified as it happens. So you're never going to get the same thing twice. And in fact, similar physical principles underlie how patterns in your skin form, like your fingerprints that you were talking about. We're going to do a little tour around some of the rest of the lab, see some of the other fun stuff we have. Can you have a laser to take home? So this is an experiment we call a dusty plasma, and it looks really complicated. We got vacuum pumps that can suck air out of our chamber here. And then what we create in here is we create a plasma, which is when you take a gas, like argon. We're using argon. Argon is something that's in the atmosphere. And we drive it with some electrical voltage, and that rips electrons away from the rest of the atom. And then they combine and they rip away, and then combine and rip away. And whenever they do that, they create light. So why don't you turn the light off real quick, Michelle, and you can come look at the purple light in here, Bobby. Sorry for the darkness. And you can see it's kind of purpley in color. That's because we're using argon gas. If we used a different gas, it would be a different color. Now what I'm going to do is turn the laser on, and you're going to see a glowing layer of green particles. And those are tiny little dust particles that are charged up because we put them in the plasma. and then we study their motion. This is called a dusty plasma. It exists on the surface of the moon, it exists in Earth's ionosphere, and it exists in our laboratory here. It's less than a human hair in diameter, but you just see them because we're scattering light. Sort of like when you have sunlight coming through the window, and you can see all the dust in your room or something like that because the light scatters from the particles. Yeah, you can see from above. You might be able to see some particles in there.
Oh, that's moving.
Yeah, now they're really getting going. I'm trying to put a lot in there.
It's like going out and in. Is that container filled with them, or how does it float in there?
I have literally like a salt shaker in there that I'm tapping. And so we study the motion of these particles. We move our camera up there, and then we actually track them in 3 dimensions. So in this chamber, it's very low pressure. Maybe pressure if you went many, many, many miles above Earth's surface, it would be sort of that kind of pressure.
So, I definitely don't want you no matter what happens. But what would happen if I stick something into the container? Like, would nothing happen?
Well, it's very low pressure in there right now, so you really couldn't stick your hand in. You'd have to wear a little spacesuit, and then we could miniaturize you, and then we could send you inside there, and you could just kind of like crawl around. Yeah, these are meant to protect your eyes from the laser light. So put these on and tell us if you can see anything green in there anymore.
No, I can't see it.
You can't see the particles anymore at all. There's different ways you can make things float. You can go in a hot air balloon, and that's density. The change in density helps you float from buoyancy. You can float in the swimming pool. These use electrostatic forces to make things float. But we're going to go over there and we're going to see how we can float things with sound waves.
That experiment was so cool, and I can't wait to do that again. Dr. Justin, how did you get into physics?
Yeah, that's a great question, Bobby. I actually, when I was your age, maybe a little bit older, I wanted to draw comic books. I was really into comic books and superheroes, and I really liked art. Then once I got into high school and started taking physics and science classes, I realized that I also love that. And you can be very creative in science, from designing experiments to visualizing data to all sorts of things. So I try to kind of put both together and do science with as much creative spirit as I can.
That is so awesome because, like, even if people don't realize it, but even when you mix paint with other things and then you paint with them and maybe it's a different texture or maybe it's a different color, that's science right there.
That's right.
But it's also being creative because you're painting. So I think that it's really cool that science is literally everyday life. Like, just driving in your car is science because you have to think, how is my car going? How is the gasoline mixing with this and stuff? And then that's science right there. So it's everywhere. And I think that's really cool that you're able to mix it together with creativity.
That's right.
How did you get into science, Dr. Michelle?
That's a great question. So when I was a kid, like your age too, and I was really into space, and I wanted to know if there are aliens. And so I was really into astrophysics and space cosmology, so I would ask people questions and read a lot of books. And also, I am a musician, so I love playing with sound and waves, and that's actually all physics as well, because it's wave manipulation. So I just wanted to learn more. But also, as a girl growing up, like, sometimes people will tell me that I couldn't do it, and that made me really mad. I was like, let me prove you wrong. So physics is just such a cool and broad subject. There's so much to learn. So yeah, and here I am.
And that sounds so awesome because I also really love space. You can probably tell because my outfit. I got stars on my pants and then a rocket right here so we can zoom around. And I think it's so sad because it's funny how people criticize girls for not doing things so much. So I think it's so cool that you can be here doing what you're doing and, like, just be able to ignore what they say. Because whenever stuff like that happens, I feel like I don't want to prove them wrong because I don't want to. They try to annoy you. They do that stuff because they try to annoy you. So you don't want to let them annoy you, but at the same time, you want to be like, you're wrong.
Exactly.
So you doing what you're doing does that in the most perfect way that it can be done.
Exactly, and maybe that's how I started. That sparked my interest, or give me a little push. But eventually, I was able to reach the space where, oh my God, I don't care what other people say, and I just enjoy science for the pure joy and discovery. And I think that is a pretty healthy place to be.
I agree. I think that science is so cool because you can go from physics to one of my favorite scientists named Mark Rober, who broke the Guinness World Record for the largest elephant toothpaste, to even just going to the hospital and thinking about how the bacteria in somebody's body reacts to the medicine that the nurses put into you. So I think it's so cool how science is literally everything. It's everything. It's even from just the air that we breathe in to how our shoes hit the ground. It's literally everything.
And one thing that we're trying to understand is how bacteria survive in the atmosphere. That's kind of like the main goal. And but in order to simulate atmospheric conditions, we had to figure out a way to levitate things in the air without touching them. And so we use something called acoustic levitation. So why don't you come over here? This is actually quite simple, something you can build at home. So all these little plastic parts were 3D printed. Just with a 3D printer we have here at Emory. And then you see all these little things here. What do those look like?
They kind of look like air vents.
Air vent. Yeah, they're speakers, actually.
They're speakers?
Yeah, they make sound, and they're all pointed at each other, right? And so, but they make sound at a very high frequency that we, us old folks, certainly can't hear. You can't hear it either. It's 40,000 hertz, which is usually above the range of human hearing. So maybe a dog or something like that could hear it, but we don't have any dogs in the lab. So, but we can levitate things with sound. So I'm just going to demonstrate. So here we have these are just styrofoam particles, the kind that might come out of a pillow that broke, in your room because you were having a pillow fight or something like that. And watch this.
Ooh. Whoa.
Here, you can hold it. So the sound waves create a series of nodes that you can visualize. Let's pull some particles up there.
Whoa.
You can twist it sideways. Yeah, they don't fall out. So the sound is levitating those particles. The original design for this was something called TinyLev, and you can, Lev mean like levitator, L-E-V. And you can find Instructables and all kinds of stuff like that. Maybe a junior or senior high school student could follow the Instructables pretty easy to put one together. For less than $100, you can build one at home. This is 3D printed, and there's all kinds of places that you can get objects 3D printed. And the speakers are very cheap. We just glued them in there with hot glue. And the idea is to just make them pointing at each other so that they all cancel each other out and make a sound node right in the middle. Or you can make a really big one, like the one that Michelle is holding.
The big left.
Yeah, we like those too, except, if something goes wrong, you have to figure out which speaker went bad, and it can be, more moving parts. So we miniaturized it here to this small version.
Does each little individual speaker matter? So like if one of them went out, would they still be able to float or would they stop?
It would work, but its performance would decrease. Here we only have 10 speakers, so it's a little bit easier for us to know if one's going wrong.
Not as well, but
upside
think
down,
about
too.
if you have a choir. If somebody is out of tune, you can maybe hear it, but it will still sound okay. But if more people are out of tune, it would sound less good and less good. So it's kind of like a choir.
So we can do one more thing, Bobby. You can hold that. Now, what do you think is going to happen when I turn the sound off?
I think it's gonna fall.
Think it's going to fall? Let's see. 1, 2, 3.
Ooh. That was satisfying.
It was satisfying.
How can we use this in the practical world?
Yeah, well, a lot of times we want to do experiments where we don't touch something, and not non-contact experiment. Maybe the thing you're handling is dangerous. Or maybe you just want to simulate an environment where something isn't touching a surface, which is what we're trying to do here. So we're using it as a pathway to do science, as a tool. Also, levitating things with sound, I think the biggest impact is the fact that somebody could make something like this at home and see some complicated yet fascinating physics all in the palm of their hand, that's probably the biggest impact.
Maybe I also want to point out is that a lot of times we don't realize that sound is just waves. So this is a really good way to kind of visualize how that would work out and how that can be applied in real life.
Thank you so much, Dr. Justin and Dr. Michelle. This has been so much fun, and I have one last question for us. If you could talk to the 10-year-old version of Dr. Michelle or Dr. Justin, what would you say?
I would say be curious and get lost and do fun things. That's the best way to find yourself.
I like that.
I would say it's okay to not know anything. You're going to feel like you don't know, and that's perfectly okay, because science is all about figuring things out.
I agree too, because like even with science experiments, like just say that you're doing like the baking soda and citric acid one where you mix them two together and it makes a volcano and stuff. Like maybe you get the variables wrong, so you put a little extra citric acid, then you do baking soda, and then maybe it doesn't erupt the way you want. But that's what the point is. Thomas Edison found 200 ways not to make a light bulb. And in case you don't want to make a light bulb, you can pick one of those 200 ways. Thank you so much, Dr. Justin. Thank you so much, Dr. Michelle. This has been so much fun, and I've never been in like a situation. I've never been in like a real lab before, and this was just so awesome to see. It looks just like the movies. And thank you to all the people who are watching this. Remember, Emory University is a college, so if you want to come here when you are in college, then you can. So thank you for watching. Bye.
Bye-bye.